to state the number of turns the graph of the function could make. So are there questions on 1 through 8 dealing with kind of determining what the end behavior is? Or are there general questions in determining the end behavior? How to do that, what to look for? Okay, so if you go to the bottom question, I guess there are 2 of them. So I want you to state the number of turns of the graph. What would like a turn of the graph mean, or what is it asking for, Greg?
Also, it's like I don't know how to explain it, but it makes like a U shape and it keeps going in the directions. But
he had an air drawing, so he gave me a little air drawing. So when you're looking at these graphs, especially the last 2 that was on like the in-class worksheet yesterday, there were a lot of like valleys and hills. So a hill, a valley is considered a turn. So a turn in the graph, we want to determine how many hills or valleys that there are in the graph. Does anybody know like what the pattern is? Do you know what the pattern is there?
Well, does it have anything to do with how many x terms there are in the problem?
Not necessarily how many x terms that there are, but the
Exponent.
exponent. So it definitely deals with the largest exponent. So the degree has a lot to do with the shape of the graph, the number of turns there are, the number of x-intercepts there would be. But how would x to the 5th determine how many turns there are in the graph? Tyler?
Isn't it n minus 1?
Yeah. So the number of turns is going to be 1 less. How about not TE, TU? So in this case, the number of turns would be 4. And the graph that I have up here kind of correlates with what it might look like.
For the turns, like, what counts as 1?
So this right here is 1. Like the peak is 1, and then the valley is another 1.
Okay. So it's like 1, 2.
3, 4.
Okay.
Yeah. So here's 1, 2, up 3, down 4. So if you go up, that's a turn, and then when you curve back down, once you kind of go down the hill, you're starting another turn. So the top number is 5, the degree is 5, therefore there are 4 turns. And then with this one over here, well, if I have negative x squared, what would that graph look like? Yeah, so that is a parabola that goes down. Parabolas, all parabolas are u's. Every power of a parabola is an x squared. All of them had 1 turn, every one that we graphed. We probably graphed like 50 different parabolas last chapter. So each of those turns, there was just 1 turn because it was a u. And that's because of the x squared. So this one would just have 1 turn. Oops. And it has 1 turn because the power of x squared, if I go 1 less than that, it would only have that 1 value. So the number of turns is 1 less than the degree. And then on the back, you were just asked to make pretty much like a general sketch. So it didn't have to be crazy, fancy, but just kind of knowing like what's going on with the equation, what the graph should look like. But if it's, I have the first one here because it's pretty much similar to the other one that we just did. But if I have x cubed and we're trying to make a general sketch, if you think of the end behavior, so if it's a positive x cubed, the whole front of the page was getting you to think about end behavior. So Jesse, if it's x cubed, that means we have an odd degree and it's positive. What's the end behavior going to be?
So left would go down, right would go up.
The left would go down, the right would go up. And then Jesse, can you give me a little air drawing of what you think this would look like?
It'd be like that.
It'd be backwards for me. So he said the left would go down, so the left has to kind of go down to negative infinity, and then the right side is going to go up. It has 2 turns because it was x cubed. So it should have 2 turns in the graph. So here's 1 turn, here's the other turn, so it has 2 turns. But the left is pointing downward, the right is pointing upward. So it didn't really have to be a specific graph, but just kind of a general shape of the graph. Are there questions? So we are going to use your calculator in a little while, so if you want to get that out, if you don't have it out. And then in your notes packets, I think it's page 21, We're gonna turn to page 21 and start the last section. On Monday, we'll finish it, wrap it up, kind of we'll do a word problem on Monday. I always like to throw in those little word problems.
Something our test is like Wednesday or something.
Your test is on Wednesday next
Oh my
week.
god.
Yes. Angelina. Sure.
I was just joking, but I mean, it's really on Wednesday.
Page 21. 23. Where's it at? So today our goal is to kind of take what we did the last 2 days with end behavior, what you did yesterday with knowing how to find an x-intercept, and see if we can get a more complete graph. We will be using the calculator's functions to help us kind of finish the graph with some of the problems, but in most of them, like if they're set up in factored form, we should be able to kind of determine a lot of it once it's in factored form, which was the worksheet you did in class yesterday. Remember, all those had parentheses, they were all in factored form. So this says that we're going to analyze the graphs of polynomial functions. We're going to talk about a zero, a factor, a solution, and an intercept. Those 4 terms all actually mean this same exact thing. So if you have a zero, a factor, a solution, or an intercept, you're really finding the same information. You're still talking about looking at an x value in the equation. So here's this huge polynomial that we talked about a couple days ago, where we have that x to the n and then n minus 1, and it goes all the way down. That dot, dot, dot means that it goes on forever until we're run out of powers, essentially. And then it ends with a sub 0. So we talked about that polynomial function, what it looks like. Remember, that just means that your powers should descend in order. So that's all that means. Don't go crazy about that it's large, huge. But the exponents are really saying they should descend in order, they should decrease. So it says if k is a real number, then the following statements are equivalent. Emerson, if something's equivalent, it is equal, the same. So there are 4 statements down below in this little box, in your box. All 4 of these statements mean the same thing, they're just worded a little differently. So the first term is a 0, and we've talked about a 0 yesterday with that worksheet. So the letter k equals 0. So if I set it up as k, how about x equals k? I'm sorry. So if I have x equals k, that is a 0 of the polynomial. We also said another word for 0 is an intercept. Essentially, you're solving for x if you're finding a 0. So a 0 of a function is also known as an intercept. But it's when I let y be 0. So if I'm letting y be 0, I'm finding a 0 of the function, or I'm finding x. And we show that x equals k because k can be any number. So x equals 5, x equals negative 2, x equals 15. So we're just using a k value here. The next term is a factor. So how does a factor usually look? So if something's factored, if we factor a problem, what does it usually look like if the problem's factored? What does it have in it to be a factor? Right?
Well, usually x plus or minus something equals 0, or equals something. I don't know. It's in parentheses.
A factor is in parentheses. So if you're factoring something, you're changing a problem into multiplication in parentheses. So a factor would look like, and as Gray said, it's usually x plus or minus something. So a factor would look like x minus 3, x plus 2, but it's in parentheses as x minus k. And he said you'd set it equal to 0, and once you set it equal to 0, then you're going back and finding the 0. So factor is in parentheses, but a factor can find the 0. A solution, if I'm solving for x and like just finding the solution, that's also in x equals form. And that was that question on the top of the page from your quiz that I just gave back to you, where it said find the real solution. So if you're finding a solution, your answer should be x equals. Well, if I'm finding a 0, my answer is also x equals. They mean the same thing. It's just I could tell you to find a 0, I could ask you to find a solution. And you just kind of have to understand that I really just need to solve for x. The last part is an x-intercept, and this is where it takes us into like the actual graphing part. K is an x-intercept of the graph, of the polynomial function, because the graph contains the point k comma 0. So when you solve for an x-intercept, you're really finding the solution, you're finding the factor, you're finding the zero. The difference with an x-intercept is that I'm then correlating it to the graph. But all of these mean the exact same thing. It just kind of depends, like the term that we're using that we're looking at. Any questions on that? So a factor is 0, is an x-intercept, is a solution. It just depends on the word that the problem's asking for. So underneath, we're going to look at our first graph here. It says use x-intercepts to graph the polynomial function. So our function has 1/4 x plus 1 quantity squared. That means there are really 2 of them sitting there, but we don't write it as separate, we keep it together. And then negative x minus 4. So use intercepts. What are the intercepts of the problem? So it's in factored form. What would the intercepts of the problem be? Right?
-1 and 4.
Yeah, they would be -1 and a +4. Now, Gray, why did you say -1 and +4?
Because it's x minus k in the parentheses, so it'd just be, if you did x, it's the opposite.
Yeah. So essentially, if you set the parenthesis equal to 0 to find x, you have to take the opposite because you have to take it to the other side. So it's always the opposite when it's in factored form. So if there's zeros, we can plot the point as an intercept of -1, 0 and +4, 0. So when you start looking at a problem and we start graphing, the first thing we want to look at is the intercepts. Graph the intercepts. They're really easy to find when it's already factored. The second thing that it tells us to do is to plot the points that are between and beyond the intercepts, because the graph has more to it than just those 2 intercepts, and we want to know where are those turns located at. So there's a little T-chart up here that's already kind of made for you, or a little table. The numbers here that are chosen are because they are beyond the intercepts or between the intercepts. So if my intercept is -1, 1 less than it would be -2. So making sure you get something on the left side of the intercept. And then my other one's 4. So I have the number 0, 1, 2, 3 here because that's between -1 and 4. And then I need to make sure I go 1 beyond the 4 as well to get, again, something on the other side of the graph past the intercept. And that way we know, does the graph go up or down? Where does it end? So using your calculator, see if you can fill in this table of values. Use the parentheses exactly as it's written. So if I'm plugging in a -2, I would have -2 plus 1 squared, and then -2 minus 4. So that's how you should plug it in your calculator. So see if you can fill in that table of values. So the goal today would be to take what we did yesterday in class, that investigating activity. Using the x-intercepts, can we now graph a couple of more points to see what the graph should look like? Question, Nate? What is -2?
Negative.
Yep, -1.5, -1.5. When you plug in a 0, this time it just doesn't cancel out like the others did. Once it's in factored form, plugging in a 0, we have to have a value. So Tyler, when we plug in a 0, you get -1. Good. And then we're plugging in a +1. Kirsten, do you have the number when we plug in a +1? Good. How about a +2? Anybody have that number? -4.5. Gunnar, you have 3.
-4.
And you have the 5th one?
Yeah.
Or 9. Good. All right, so we're going to then kind of look at the next question, or the next piece. So the first step, quickly find the intercepts. The second step, make a table of values getting points that are less than or greater than beyond the intercepts and then in between. And then the third step says determine the end behavior. So there's a whole bunch of mumbo jumbo underneath here. We're going to skip all that mumbo jumbo, and what I need you to remember with the end behavior is how we've been writing it. So what does the left do? What does the right do? So if you look at the leading coefficient and the degree, how do I know what the power would be of this graph? Jesse?
How many X's there are?
How many x's there are. Now be really careful because this quantity is squared, Jesse, so really that means there are
There's two there.
2 here. So right here there are 2 x's and then there's one more. So Jesse, it would be
Three.
x, yeah. So it would be x cubed. And what's the leading coefficient, the number in front of the whole thing? A 1/4. So it has 3 factors because x plus 1 is a factor, x plus 1 is a factor, x minus 4 is a factor. So that's why there are 3 factors there. So the leading coefficient is 1/4. We would say that this is odd and positive because 1/4 is a positive number. So Jesse, what does that tell us then about the end behavior?
That means the left would go down, the right would go up. Right?
The left would go down and the right would go up. So when it's odd and positive, the left goes down, the right goes up. Odd, the graph always splits. So then the last thing we're going to do after we have that information is try and graph it. So starting with your intercepts, we're going to plot those points. So we had one at -1 and the other one at +4. Take your table of values, plot those as well, and then we'll see if we can apply the end behavior. And I know the last one doesn't fit on the graph, just put it kind of way high up, because the last one was 5, 9. So Jesse said that the left should go down. So if you go to your farthest point on the left side, make that go down. Because that should be my end behavior. So from the furthest left point, the graph should go below that furthest left point. And then we're connecting the dots. So we're going up to the intercept. And then my next point is below that. So I'm going to continue connecting the dots. The right should go up. The end behavior was left down, right up. Nate.
What's the difference between like odd positive and even positive?
Even positive, they both go up or they both go down. So even graphs, both sides do the same thing. Where an odd graph, it splits. So one side goes down, the other side goes up. So even graphs, they either both go up or both go down. They go the same direction, both sides. Other questions? Does anybody remember what the domain is? How to find the domain? What letter the domain is? All the x values. There were 2 different ways that we looked at that. So Emerson, x is left and right. So how far left and right does this graph continue to spread? Get wider, get wider.
-2 to 5.
So on our graph, it's -2 to 5.
So it's just, it's
It's infinite. So we wrote that 2 different ways. Do you remember how we wrote that if it was infinite?
no.
We used a symbol. Gunnar?
Positive.
So we could write it as -infinity to positive infinity, but we also used a symbol. Ethan?
It's the R.
Yeah, it's the R with 2 lines. So we used both of those, and I know this was it was chapter 2 when we talked about this. It was a while ago. In chapter 6, we're really going to look at domain and range again. So it's been a while since we've talked about it. But -infinity to positive infinity, that just says it keeps going on forever. Or you could say the all real numbers. And then the range is the y. So from the bottom of the graph to the top of the graph. So this is going down forever on the bottom. The top is going up forever. So again, you could say -infinity to positive infinity. Or you could just say that R with the double line. Not the paragraph symbol, but in math it's the all real numbers symbol.
So wouldn't that be true for
All
all continuous functions?
For the domain, yes, but the range might not. because like if you think of the W graph has a max point, because it either goes below that or above that. Other questions, Jesse?
Would it like would it like slow its curve like a
The curve would slow down, yes. So at a point, it's just gradually, like minimally, going to get wider and wider, but it never goes vertical. So it still will just
So
continue to get.
So like, is there a way to find like the border, like how like in like an square function, you can find the line that like never passes?
There is never a line that it never passes. It just continually, just gradually gets wider and wider. So it'll never be completely vertical. So there is no border or boundary. Okay.
Okay, so I'm really bad making the all real numbers R.
Yeah.
Can I just write all real numbers in
Sure.
words?
Yeah, or you can just write negative infinity or positive infinity, or you don't like writing those either.
I don't like writing those either.
No, okay. You can write it in words, that's fine. Any other questions? Good questions. Alright. So if you flip it over, we're going to see if we can do another one. So we're going to think about the same thing as we work through the problem. When you came in, you picked up a little quarter sheet of paper. This quarter sheet of paper has directions as to how you'll graph from the homework. So every problem, you're going to be finding essentially the same things that we just did. So the first thing is to list the intercepts. The second thing would be then to think about, like, what's the end behavior? Can I make a t-chart? But this little sheet is what you need to use when you're doing your homework tonight. So the steps on here for graphing are the same steps that we just went over. So the first thing that we're going to think about would be the zeros, because that's the first thing we found with the other problem. And that's really easy to find because it's already factored. So Tyler, the zeros, Tyler W, are?
2, -1.
Yeah, so 2, -1, and +1. And then we're going to take these and make a little t-chart or a little chart. And if you want your chart to go vertical, that's fine. But you can make the horizontal chart as well. So the numbers we pick need to be less than and greater than my 2 zeros, and then in between them. So my 0 at -1 is the smallest, so I need to make sure that we go less than it. And then we would need a 0 for x. We already have the 1 and the 2, so maybe we'll make a 3, and maybe we'll go one more to make a 4 as well, just to get a couple of values. So you want to make sure that you're going less than and greater than the zeros, and then in between them. So we'll be finding the zeros, making a table of values, getting the end behavior, plotting and connecting our points. Anyone have values for the t-chart? What do you have, Gunnar?
-24.
Yep.
4, 16, 60.
So they get pretty big, so it's going to be a little tricky to graph those. Last thing we're going to think about is what the end behavior would be. So looking at the numbers up here, the x's. John, how many x's do we have in the problem? 3. So x cubed, and the number in front is a 2. So again, we're dealing with it being odd and positive. So John, the left side and the right side for the end behavior,
The left goes down, and the right goes up.
and the right goes up. And that should correlate with the points that we have. So if we look at the zeros, plotting those points, 2, 0, negative 1, 0, positive 1, 0. And then the first point in our table of values, negative 2, negative 24, I mean, that's really, really low. Just make sure that you know that you're going to have a point because it should, the left side should go down. And then at 0, we have a point of 4. And then 3, we have a point at 16. And I'm not even going to think about trying to graph 4 and 60. So the left side should go down, which is why negative 2 has a value at negative 24. And then it's going to continue to go all the way up. And then once I hit that point, I need to come down. What do you think you do in between the two zeros? Gunnar? Yeah, we need a little hook here. It can't be flat. These are all curves. So we need a little hoop or a little turn to go underneath, then to spin back and connect to the other 0. And then it goes all the way back up. So remember, these should be curves, turns, hills, valleys. It's never just flat, horizontal. So it needs to, if you have two zeros next to each other, it has to go underneath and go back up to connect to the next one. Any questions? So the last thing, it says what is the domain and the range. This one is like very similar to the graph we just did. So negative infinity to positive infinity. We're writing all real numbers either way. But there is no stopping point. There's no point where it just stops. It just continues to gradually continue to get wider and wider and wider. All right, so questions with the graphing. There are two terms below those graphs. There's a little diagram drawn over here. And two words here talking about a local maximum and a local minimum. And in the diagram, it shows you the local maximum is essentially the top of the curve. The local minimum is the bottom of the curve. So when you're talking about a max or a min value, generally we say it's like the largest point of the graph, or just the largest value of anything, of any function. The reason it's called a local maximum is because the largest point in my graph is negative infinity or positive infinity. The local minimum, the smallest point in my graph, would be negative infinity. But we're not really looking at those because that's the end behavior. So the local maximum would be, you could say, like the top of your turning point or the highest value of your turning point. I'm going to say the largest y of the turning point. So a turning point is the same thing as that curve in your graph. So the local maximum is the highest part of that curve.
So technically, like, say I put it into my calculator and not the whole thing fits, and like I only see that, but there's like another loop like outside of it. Wouldn't that technically be the local one, or would the local
Yes.
one be the one you can see?
Nope, it would be both of them. Any top value of any turning point. So you have to you'll have to change your calculator to make sure you could see it all.
Okay.
So yesterday we put that 0.2 in front of the graph to make sure that we could see it all. So the local minimum is the lowest y value of the turning point. And the key thing that like Gray was talking about, you can have more than one local minimum, more than one local maximum. So like I could have 2, I could have 3. It depends how many turning points you have. So if I have a couple of hills, then all of those are maximum values. The last part at the bottom of the page here talks about those turning points. The graph of every polynomial function of degree n has at most n minus 1 turning points, which is I think what Tyler said while we were going over the homework. So if it's an x to the 5th, then x to the 4th is that n minus 1 value. If you have n real zeros, then you have exactly n minus 1 turning points. So I do want to show you how to use the calculator. I have like 3 minutes and I want to try and squeeze this in. So we're going to use the calculator to graph. There is a little picture already drawn, but if you can keep that calculator out, go to your y equals. So we're plugging in x cubed. You can use a little caret. You can use math. Number 3, either one works, but the little caret is quickly how you can get the x cubed. And then we have minus 4x squared. And then it says plus 6. So if you hit the graph button, this is what my graph looks like, which exactly like what's shown in the picture below. Does anybody remember how we use the calculator to find max and min values? Gray, do you remember?
So you press the second calculate, and then you're gonna do. I forget actually.
Yeah, you're good. So he said second calculate, that's at the top. Trace is at the top next to the graph. And then either you're finding a minimum or a maximum. So if we want to find, we'll say the minimum first. I'm going to press number 3. And then I have this little blinking buddy. That little blinking guy, you need to arrow down to where the minimum part is. The left bound means your little blinking guy should be on the left side of it. So right now it looks like it's pretty much slightly on the left. Hit enter. Right bound means my little blinking guy has to be on the right side of where I think the lowest point is. And then hit enter. Never do anything for guess. You just hit enter one more time. And then it says we have a minimum at 2.6 repeating and negative 3.48. So you can write those down for that graph. There should be a little blank for that. If I want to find the maximum, I just go back and do number 4. Again, that little blinking buddy, now he needs to be to the top of my turning point. Left bound means it should be on the left of it. So I want to be on the left side of it, and then right bound be on the right. The last 2 problems of the homework, you'll be given an equation and asked to use the calculator to find the max and min value. Have an awesome weekend. Please, when you're graphing, follow those steps on that sheet.